valence band edges driven far from the Fermi level, and holes from the body are driven away from the gate. At larger gate bias still, near the semiconductor surface, the conduction band edge is brought closer to the Fermi level, populating the surface with electrons in an inversion layer or N-channel at the interface between the P region and the oxide. This conducting channel extends between the source and the drain, and current is conducted through it when a voltage is applied between the two electrodes. Increasing the voltage on the gate leads to a higher electron density in the inversion layer and therefore increases the current flow between the source and drain. For gate voltages below the threshold value, the channel is lightly populated, and only a very small subthreshold leakage current can flow between the source and the drain. When a negative gate source voltage, positive source gate, is applied, it creates a P-channel at the surface of the N region, analogous to the N-channel case, but with opposite polarities of charges and voltages. When a voltage less negative than the threshold value, a negative voltage for the P-channel, is applied between a gate and source, the channel disappears and only a very small subthreshold current can flow between the source and the drain. The device may comprise a silicon on-insulator device in which a buried oxide is formed below a thin semiconductor layer. If the channel region between the gate dielectric and the buried oxide region is very thin, the channel is referred to as an ultra-thin channel region with the source and drain regions formed on either side in or above the thin semiconductor layer. Other semiconductor materials may be employed. When the source and drain regions are formed above the channel in whole or in part, they are referred to as raised source /drain regions. Comparison of N and P-type MOSFETs. 5. Parameter MOSFET /drain type N-type of type E-channel type, MOS capacitor, N-type of type gate. Type polysilicon and P and metal Si conduction band Si valence band well type of type N type E threshold voltage, VTH positive, enhancement. Negative, depletion. Negative, enhancement. Positive, depletion. Band bending downwards upwards inversion layer carriers electron show less substrate type of type N type. Modes of operation. Source tied to the body to ensure no body bias. Top left, subthreshold. Top right, ohmic mode. Bottom left, active mode at onset of pinch off. Bottom right, active mode well into pinch off. Channel length modulation evident. The operation of a MOSFET can be separated into 3 different modes, depending on the voltages at the terminals. In the following discussion, a simplified algebraic model is used. 7. Modern MOSFET characteristics are more complex than the algebraic model presented here. 8. For an enhancement mode, N-channel MOSFET, the 3 operational modes are Q-TAF, subthreshold, and WEC inversion mode when VGS and LTVTH, where is gate to source bias and is the threshold voltage of the device. Example application of an N-channel MOSFET. When the switch is pushed, the LED lights up. 6. According to the basic threshold model, the transistor is turned off, and there is no conduction between drain and source. A more accurate model considers the effect of thermal energy on the Fermi-Dirac distribution of electron energies, which allow some of the more energetic electrons at the source to enter the channel and flow to the drain. This results in a subthreshold current that is an exponential function of gate source voltage. While the current between drain and source should ideally be 0 when the transistor is being used as a turned-off switch, there is a weak inversion current, sometimes called subthreshold leakage. In weak inversion, where the source is tied to bulk, the current varies exponentially with as given approximately by SAD Smiley 9, 10, where equals current at the thermal voltage and the slope factor N is given by with equals capacitance of the depletion layer and equals capacitance of the oxide layer. This equation is generally used but is only an adequate approximation for the source tied to the bulk. For the source not tied to the bulk, the subthreshold equation for drain current in saturation is 1112, where the is the channel divider that is given by with equals capacitance of the depletion layer and equals capacitance of the oxide layer. In a long channel device, there is no drain voltage dependence of the current once, but as channel length I reduced drain-induced barrier lowering introduces drain voltage dependence that depends in a complex way upon the device geometry, for example, the channel doping, the junction doping and so on. Frequently, threshold voltage VTH for this mode is defined as the gate voltage at which a selected value of current ID0 occurs, for example, ID0 equals 1A, which may not be the same VTH value used in the equations for the following modes. Some micropower analog circuits are designed to take advantage of subthreshold conduction. 13, 14, 15. By working in the weak inversion region, the MOSFETs in these circuits deliver the highest possible transconductance to current ratio, namely, almost that of a bipolar transistor. 16. The subthreshold IV curve depends exponentially upon threshold voltage, introducing a strong dependence on any manufacturing variation that affects threshold voltage. For example, variations in oxide thickness, junction depth, or body doping that change the degree of drain-induced barrier lowering. The resulting sensitivity to fabricational variations complicates optimization for leakage and performance. 17, 18. MOSFET drain current versus drain to source voltage for several values of the boundary between linear, ohmic, and saturation, active modes is indicated with upward curving parabola cross-section of a MOSFET operating in the linear, ohmic, region. Strong inversion region present even near drain cross-section of a MOSFET operating in the saturation, active, region. Channel exhibits channel pinching near drain triad mode or linear region, also known as the ohmic mode. 19, 20, when VGS and GT VTH and VDS and LT. VGS VTH, the transistor is turned on, and a channel has been created which allows current between the drain and the source. The MOSFET operates like a resistor, controlled by the gate voltage relative to both the source and drain voltages. The current from drain to source is modeled as where is the charge carrier effective mobility, is the gate width, is the gate length and is the gate oxide capacitance per unit area. The transition from the exponential subthreshold region to the triad region is not as sharp as the equations suggest. Saturation or active mode. 21, 22. When VGS and GT VTH and VDS greater than or equal to VGS VTH, the switch is turned on, and a channel has been created which allows current between the drain and source. Since the drain voltage is higher than the source voltage, the electrons spread out, and conduction is not through a narrow channel but through a broader, 2- or 3-dimensional current distribution extending away from the interface and deeper in the substrate. The onset of this region is also known as pinch-off to indicate the lack of channel region near the drain. Although the channel does not extend the full length of the device, the electric field between the drain and the channel is very high, and conduction continues. The drain current is now weakly dependent upon drain voltage and controlled primarily by the gate source voltage, and modeled approximately as the additional factor involving lambda. The channel length modulation parameter models current dependence on drain voltage due to the early effect, or channel length modulation. According to this equation, a key design parameter, the MOSFET transconductance is where the combination VUF equals VGS VTH is called the overdrive voltage, 23, and where VDSAT equals VGS accounts for a small discontinuity in which would otherwise appear at the transition between the triodion saturation regions. Another key design parameter is the MOSFET output resistance route given by route is the inverse of GDS where ID is the expression in saturation region. If lambda is taken as 0, an infinite output resistance of the device results that leads to unrealistic circuit predictions, particularly in analog circuits. As the channel length becomes very short, these equations become quite inaccurate. New physical effects arise. For example, carrier transport in the active mode may become limited by velocity saturation. When velocity saturation dominates, the saturation drain current is more nearly linear than quadratic in VGS. At even shorter lengths, carriers transport with near-zero scattering, known as quasi-ballistic transport. In the ballistic regime, the carriers travel at an injection velocity that may exceed the saturation velocity and approaches the Fermi velocity at high inversion charge density. In addition, drain-induced barrier lowering increases off-state QTAF current and requires an increase in threshold voltage to compensate, which in turn reduces the saturation current. Body effect. Band diagram showing body effect. VSP splits Fermi levels Fn for electrons and F for holes, requiring larger VGB to populate a conduction band in an NMOS-MOSFET. The occupancy of the energy bands in a semiconductor is set by the position of the Fermi level relative to the semiconductor energy band edges. Application of a source to substrate reverse bias of the source body p-n junction introduces a split between the Fermi levels for electrons and holes, moving the Fermi level for the channel further from the band edge, lowering the occupancy of the channel. The effect is to increase the gate voltage necessary to establish the channel, as seen in the figure. This change in channel strength by application of reverse bias is called the body effect. Simply put, using an NMOS example, the gate-to-body bias VGB positions the conduction band energy levels, while the source-to-body bias VSB positions the electron Fermi level near the interface, deciding occupancy of these levels near the interface, and hence the strength of the inversion layer or canal. The body effect upon the channel can be described using a modification of the threshold voltage, approximated by the following equation, where VTB is the threshold voltage with substrate bias present, and VT0 is the 0 VSB value of threshold voltage, is the body effect parameter, and 2B is the approximate potential drop between surface and bulk across the depletion layer when VSB equals 0 and gate bias is sufficient to ensure that a channel is present. 24, as this equation shows, a reverse bias VSB and GT0 causes an increase in threshold voltage VTB and therefore demands a larger gate voltage before the channel populates. The body can be operated as a second gate, and is sometimes referred to as the back gate. The body effect is sometimes called the back gate effect. 25, circuit symbols. A variety of symbols are used for the MOSFET. The basic design is generally a line for the channel with source and drain leaving it at right angles and then bending back at right angles into the same direction as the channel. Sometimes 3 line segments are used for enhancement mode and a solid line for depletion mode. See depletion and enhancement modes. Another line is drawn parallel to the channel for the gate. The bulk or body connection, if shown, is shown connected to the back of the channel with an arrow indicating PMOS or NMOS. Arrows always point from P to N, so NMOS, N channel in P well or P substrate, has the arrow pointing in, from the bulk to the channel. If the bulk is connected to the source, as is generally the case with discrete devices, it is sometimes angled to meet up with the source leaving the transistor. If the bulk is not shown, as is often the case in IC design as they are generally common bulk, An inversion symbol is sometimes used to indicate PMOS. Alternatively, an arrow on the source may be used in the same way as for bipolar transistors, out for NMOS, in for PMOS. Comparison of enhancement mode and depletion mode MOSFET symbols, along with JFET symbols. The orientation of the symbols, most significantly the position of source relative to drain, is such that more positive voltages appear higher on the page than less positive voltages, implying current flowing down the page. SAD Smiley 26, 27, 28. P-channel JFET P-channel labeled.svg. IGFET PCHN labeled.svg. IGFET PCHN labeled simplified.svg. MOSFET PCH Cedra.svg. IGFET PCH dip labeled.svg. N-channel JFET N-channel labeled.svg. IGFET NCHN labeled.svg. IGFET NCHN labeled simplified.svg. MOSFET NCH Cedra.svg. IGFET NCH dip labeled.svg. JFET MOSFET N.MOSFET N. No bulk, MOSFET dip. In schematics where G, S, D are not labeled, the detailed features of the symbol indicate which terminal is source and which is drain. For enhancement mode and depletion mode MOSFET symbols, in columns 2 and 5, the source terminal is the one connected to the triangle. Additionally, in this diagram, the gate is shown as an L shape, whose input leg is closer to S than D, also indicating which is which. However, these symbols are often drawn with a T-shaped gate, as elsewhere on this page, so it is the triangle UHIC must be relied upon to indicate the source terminal. For the symbols in which the bulk, or body, terminal is shown, it is here shown internally connected to the source, i.e., the black triangles in the diagrams in columns 2 and 5. This is a typical configuration, but by no means the only important configuration. In general, the MOSFET is a 4-terminal device, and in integrated circuits many of the MOSFETs share a body connection, not necessarily connected to the source terminals of all the transistors. Applications. Digital integrated circuits such as microprocessors and memory devices contain thousands to millions of integrated MOSFET transistors on each device, providing the basic switching functions required to implement logic gates and data storage. Discrete devices are widely used in applications such as switch mode power supplies, variable frequency drives and other power electronics applications where each device may be switching thousands of watts. Radio frequency amplifiers up to the UHF spectrum use MOSFET transistors as analog signal and power amplifiers. Radio systems also use MOSFETs as oscillators, or mixers to convert frequencies. MOSFET devices are also applied in audio frequency power amplifiers for public address systems, sound reinforcement and home and automobile sound systems MOS integrated circuits. Following the development of clean rooms to reduce contamination to levels never before thought necessary, and of photolithography, 29, and the planar process to allow circuits to be made in very few steps, the SiO2 system possessed the technical attractions of low cost of production, on a per-circuit basis, and ease of integration. Largely because of these two factors, the MOSFET has become the most widely used type of transistor in IET. General Microelectronics introduced the first commercial MOS integrated circuit in 1964. 30. Additionally, the method of coupling two complementary MOSFET, P-channel and N-channel, into one high forward/low switch, known as CMOS, means that digital circuits dissipate very little power except when actually switched. The earliest microprocessors starting in 1970 were all MOS microprocessors, i.e., fabricated entirely from PMOS logic or fabricated entirely from MOS logic. In the 1970s, MOS microprocessors were often contrasted with CMOS microprocessors and bipolar bit slice processors. 31. CMOS circuits. The MOSFET is used in digital complementary metal oxide semiconductor (CMOS) logic. 32, which use ISP and N-channel MOSFETs as building blocks. Overheating is a major concern in integrated circuits since ever more transistors are packed into ever smaller chips. CMOS logic reduces power consumption because